Well, hi everyone. I'm a 2016 fellow, and so I am currently a postdoc at ASU, and I was also a graduate student there. And actually the reason I'm still at ASU is in large part because of the Blue Waters project that I worked on. So what I'm going to talk to you about today is mostly a product that came from Blue Waters, but there's also a kind of a core idea that I think is neat, and hopefully at least one person in the audience, or we'll say, yeah, one other person than myself will think it's cool. So I'll say up front, a bit of it might be a bit technical, but I think I'll be able to keep you guys with me if you can kind of just hear the high-level language I'm working with. So I'll start the story. So basically, I am not interested in, as a graduate student, I wasn't interested in hydrodynamics. I was interested in the so-called structure-function connection of proteins. So this is like an enzyme, and you could see it had those fading substrates that would be bound by these colored movable domains. And the whole point of what I was trying to do was to understand how this works based on how it moves. But the idea is that it moves based on its structure from the physics. And so finding that connection was the key to my research. Now, I was also interested in things like membrane transporter proteins. So they also undergo large-scale conformational changes, and their purpose is to transport stuff across cellular membranes. So the time scale of these processes is what makes people look for allocations in supercomputers. So they take place on microseconds if you're lucky, but it's more like milliseconds and sometimes beyond that. And the issue is if you really want to capture all of this heterogeneous detail, then you actually have to care about the environment. And so it's mostly water. I mean, there's junk in the cell and so on, but it's dense. And if you want to do a molecular dynamics simulation where you just follow Newton's laws, well, then you have to calculate the forces between all the atoms. And these force calculations are incredibly expensive when you have many of these solvent particles to worry about and not as much of the actual protein of interest. Now, if you have this level of detail, the key issue is that you basically need to take on the order of femtosecond time steps. And it's because the fastest time scales in the system are bond oscillations, which are on the order of 1 to 10 femtoseconds, depending on whether or not you add constraints. So basically, you're kind of screwed if you want to observe transitions happening on the millisecond time scale, unless you have some very specialized machine. And moreover, you're not even going to observe many of these transitions. So forget statistics, right? So if you want to compute rates, you're going to see 3 of these events. You might get some insight into the atomistic detail, right? But it's like moving a bike handle, and you can see, oh, I see how that moves. But you may not actually know the process by which the actual motions are triggered or take place. Okay, so there's this enormous computational problem, and there's a reason why biophysicists use up Qs. Atomistic simulations are incredibly expensive. So this motivated my Blue Waters project, which was to investigate hybrid atomistic continuum simulations. So the idea is rather simple. So if you have some solute and you have some surrounding solvent, then the idea is you resolve the solvent where you need the detail, where you want to resolve the forces, but then you put this continuum hydrodynamic representation on the outside, so you can still capture the flows, but you don't have nearly the computational cost of calculating all these forces explicitly. Okay, so this seems really easy in principle. You do have to be very careful about how you stitch these boundaries, but since I'm talking about it at a high level, this doesn't actually seem like a challenge. So you just say, mass, momentum, energy conservation across this boundary, and if you don't care about how you calculate it, it seems easy. Okay. I'll also say, we'll come back to this, you also need to care about fluctuations. So you need a special solver for this. But the basic high-level idea is rather pretty. You put a protein in a blob of detailed atomistic water, and then you have a fluid simulation updating on the outside. And you can even switch cells from atomistic to continuum and back and forth. Okay, that's like the pipe dream, but this is hard. So there are people who have done basic things, but whether or not you can get a full-scale simulation working like this and then get the physics correct across the boundary, that's a different question. Now, one thing I wanted to say before I go into this fluctuating hydrodynamics that I pointed out is that hydrodynamics is not merely just a good way of saving computational expense when you do an atomistic simulation. It's actually relevant at shorter length scales than a lot of people expect. So I very often get questions like, well, isn't it low Reynolds number? Not much stuff is happening, everything's sticky. So just to give you a qualitative example, here's a simulation that I ran with a code that I developed for Blue Waters. And it can do 2D turbulence. So this is reasonably high Reynolds number flow. And the only thing I want you to gather here is that it's swirly. But you can actually take a simulation of a lipid bilayer. So this is like a cell membrane. And these hydrophobic tails in the middle, there's not much friction between them. So these layers can slide rather easily. And if you take a top-down view of a MD simulation, coarse-grained, you see this swirly behavior. And we're only talking, that's 100 nanometers. So, I mean, it depends on the physics you're looking at. If you're looking at lipids or water, will you see really swirly effects? Point is, though, this is happening below the scale of a cell, which we might want to say is micron-ish. Okay, well, I actually want to go beyond that. And to get there, I'm going to just talk qualitatively about hydrodynamic conservation equations. So the basic idea is that you just have some conserved quantity phi, and then you have some source of that. So if it's being created or destroyed, you have something over here. And the rate of change of that thing just depends on whether or not it's leaving that region of space. Is it spreading out or coming in? So you play the game with mass, if that's what you want to conserve, and then you get the familiar continuity equation. Almost all of us are probably familiar with this. And you can do this with momentum and energy. And I'm leaving out, for those who know, I'm leaving out heat flux here, just to keep things simple. What I have put in here, though, is the sigma, the stress tensor. And so for those who do fluid mechanics, you're going to know that a Newtonian fluid will have this relationship of stress being proportional, eta being the viscosity, proportional to the shear, the rate of strain in the flow. Now, one thing I said you had to do is care about fluctuations. So if you want to do a hybrid simulation and you neglect fluctuations, it turns out you're going to get a lot of quantitative and qualitatively wrong answers. Conveniently, there's a prescription for doing this, and it was done by Landau-Lifshitz in like the 60s. So if you have stresses, you can put this fluctuating stress tensor in here that actually captures the granularity that's happening, all the collisions and the statistical granularity. And when you put this into a simulation, so if you look on the right, this is where the fluctuations have been put in, and on the left, you don't have it. And this is just a simple jet flowing to the right. It's like a meter per second. And uniform density, and if you let it go, you should see that perturbations in the flow here grow faster. Not to mention that there are also perturbations constantly being fed in through the stress tensor. Okay, so one thing I will point out that's kind of interesting is you kind of get a chunkiness, whereas this seems to be smoother and it doesn't kind of form these blobs. So droplet breakup is actually an important thing that people look at, and it has a lot to do with thermal fluctuations. The only point I'm trying to make in general, though, is that if you don't put the fluctuations in, you can get completely wrong answers qualitatively. Okay, so, oops. So, I mean, I've already talked about that, but what I now want to think about is if I'm really trying to do a hybrid simulation where I'm talking about those proteins that you guys saw in the beginning, how am I actually going to make those boundary conditions work? All right, so the proteins you saw in the beginning were like 5 nanometers, maybe 10, maybe a little bit over that. Okay, so if you're stitching together a continuum and a particle simulation, and you want to get rid of solvent, well, you don't want to put the fluid simulation boundary far away, because then you're not deleting the solvent, and that's the whole point, right? So you want to put it really close. So as I was trying to do some of these test simulations, I was using a grid on top of these particles that was on the order of a nanometer, just for the heck of it. And waters are like 3 angstroms in size. Well, there's obviously a physical problem here. So just to point out a few things, first of all, fluctuations become enormous. So as your cell volume gets smaller, fluctuations grow. Same with the time step, which needs to get smaller because you're resolving larger fluctuations. And so we're just obviously violating things that you would think would need to not be violated in order to use the continuum approximation, right? So we're on the order of the collision time of the particles, and we can even resolve the spacing. So this seems too granular. So one question you might ask is the stress instantaneously proportional to the rate of strain? In other words, does the fluid look Newtonian when you're at this scale? Okay, so I already put in the thermal fluctuations. The argument is that you actually need to go beyond that. So the stress, perhaps you would write down as an ansatz, should be time dependent. And what I've done is introduce here this microscopic collision time. So this really is like the mean time between collisions of the particles. Now, I'm not going to justify this just yet, or maybe I don't even have time to, but I'm going to make this argument that I think is rather nice and it has practical use. So before I get there, I just want to point out that I have 10 total equations. Okay, so it seems like I've added more stuff. It seems like this is more expensive than computing what you would normally do for Navier-Stokes. So I just want everyone to keep that in mind. And now let's take a closer look at the stress equation. So if I were to discretize this, now I'm not going to, well, let me say this first. For those of you who are familiar enough with numerical algorithms, you know that if this tau is small, that I'm not going to be able to integrate this normally with like an explicit solver, right? So it's going to be numerically stiff, and the simulation is going to go unstable. Okay, so if I were to advance the simulation with one of these implicit in time methods, meaning literally everything is determined, all these quantities here are determined at a later point in time, and then I have to solve it implicitly, then I could get a stable numerical simulation. Okay, so what's the point, right? Why am I saying this? Well, if you trust my algebra, you get something that starts looking like this, and that's a lot of stuff to stare at, but don't really stare in too much detail. Just consider what happens if I make my time step larger than the collision time. So what I'm saying is I'm literally stepping over the collision time, and I'm choosing to be ignorant of the detailed physics. Okay? If I do that, well, then what you see is that this term is 0, that term is 1, and what I get back is Navier-Stokes. So what I actually have now is a clever way to solve Navier-Stokes, where I don't actually have to bother doing, all the complicated methods with pressure, blah, the things that confuse me. This is actually the way I got around dealing with second-order derivatives, for instance, second-order spatial derivatives. And it turns out it's actually not that, it's actually just as fast, if anything. The advantage of this is that somehow maybe extrapolating gets you some useful physics. Okay, so here are all the equations now. And what I'm proposing is that you can do something like this, where you move the stress term as a source term in this equation. And now we have our nice mass, momentum, and energy conservation. So I have zeros on the right-hand side. So they're in nice conservation form. And then I have this stochastic equation. It's a Langevin equation for the stress. I can also add in heat flux, and then I get this so-called 13 moment approximation. So the theory actually has been worked out for, the full nonlinear theory actually has been worked out in like 1940s or late 1940s. Harold Grad. And this is actually the approach I took and I am taking to do fluctuating hydrodynamics, where I intentionally choose tau to be smaller than my time step. The question I'm really interested in and trying to work on is how good is this approximation when delta t is comparable to tau? So how good is this approximation in resolving the physics with my time step? Okay, so the part for blue waters here, what came out of this can be just stated as this product called HERMESHD. So this is the code that I developed. The point being that it not only allows you to do this Landau-Lifshitz Navier-Stokes, which is Navier-Stokes with fluctuations, it goes beyond that potentially. Another thing, for those who are familiar with the fluid physics, this goes beyond this diffusive picture where you have momentum diffusion and heat diffusion, and you actually have finite transport speeds. And that's because you actually you're moving away from these Laplacians that look like diffusion equations. And what you get are these equations where I put in the time dependence, and now they can carry waves. right? So it's more physically, I guess, desirable. But the most interesting thing to me, and I think the most useful thing, is that your physics is dictated by the time step. So the point is to literally use the time step as your observation scale. Now, I mean, these are small technical bits about the code that I personally don't care too much about, at least not for this talk. But the code is based on a discontinuous Galerkin representation. All that you guys really need to know is that I am avoiding so-called higher order finite volume methods. So I don't have to go to second order methods where I'm required to calculate derivatives by looking at the next nearest neighbor of a cell or even farther out. Now, this actually was incredibly helpful on blue waters because when I was breaking apart the domain of my fluid domain, and then sending them out to different nodes and so on, the communication costs were actually rather high when working with the higher order methods. But you don't have to worry about that here. So if you have a discontinuous Galerkin method, and I have these fancy time-dependent stress and heat flux equations that I'm solving implicitly with a large time step, I'm just solving Navier-Stokes, but I'm solving it locally in space and time. So it's actually a rather frugal way to do simulations when communication costs are large. Right now, it's completely built on Fortran 90. And I'm working on a Python interface to make it accessible to people other than myself. I mean, you can look at it. It works if you kind of know what you're doing, but it's obviously a work in progress. But if you guys do want to check it out, I mean, it's on Bitbucket. It should be publicly available. And I guess with that, I'd like to acknowledge my PhD advisor, Oliver Bechstein, who's at ASU, for even letting me pursue this in the first place. It's kind of orthogonal to what I was originally doing. So my father, Charles Seyler, who's at Cornell, he's the one who lent me basically the starting bit of the code. So the code that I'm working with is a stripped plasma physics code. So basically I asked him to give me the hydrodynamics. And he was nice enough to spend quite a bit of time stripping it. I had actually worked with the code before as an undergraduate. But anyways, he spent an awful lot of time helping me with the technical bits. I would not have been able to figure out the Fortran 77 that's hiding in there. So obviously, thank you to my father. And then my current advisor, who was nice enough, Steve Pressay, who's also at ASU, who even let me come here in the first place to talk about something that has nothing directly to do with my research now. And then, of course, none of this would have happened at all without Blue Waters.